Hi, this is Professor Fernandez, and in this video we're going to work on example 3.11 from Calculus to Simplified. This example asks us to find the volume of this solid, actually to set up and not evaluate the integrals yielding the volume of this solid. Given information about the region, the functions, but where the cross sections parallel to the x-axis, not perpendicular, are three different types. So squares, semicircles, and equilateral triangles. So we'll be setting up three integrals here. Okay, first thing to know is that because we're going with cross sections parallel to the x-axis, right? If I zoom in here, all of the infinitesimal rectangles that are going to form the base of these cross sections are horizontal. They're not vertical infinitesimal rectangles, like would be the case for cross sections perpendicular to the x-axis, right? So these infinitesimal rectangles are parallel to the x-axis. Okay, parallel infinitesimal rectangles means that we're going to want our functions to be functions of y. So that's why the information in the prompt is giving us functions of y. One of these, x equals y, is this one. It's the linear function. The other one, x equals cube root of y, is the nonlinear function, right? So that's this one. Okay, so that's going to help us because up here is where this region is going to stop. So this is going to be the base of the solid that we are going to construct. And you see the solid over here. And that tells us, therefore, that the smallest y value is y equals 0. And the largest y value here is y equals 1. So our volume of our solid is going to be integral from 0 to 1. And we have to find the area of a cross-sectional slice. So the base of that slice is this infinitesimal rectangle, and the rest of the slice, the height, is going to depend on whether it's a square, whether it's a semicircle, or an equilateral triangle. So we'll get there in a minute. I just want to point out this integral that I'm using here, where it came from. So this is theorem 3.4 in the book. So feel free to pause the video here if you'd like to take a look. But long story short, if you know your smallest c value, your smallest d value of the 2D region, right? In our case, it's this region here, y equals 0 and y equals 1. Those are our c and d values. If you know those values, right, then you set up your integral from c to d of a of y dy. And a of y is, again, the area of one of these cross-sectional slices, either a square, triangle, semicircle, or whatever other shape it has. Okay, so further in the book, right, in figure 3.7, I actually collected all these different area formulas for the standard cross-sections that you might be asked for, like squares, semicircles, or equilateral triangles. And so I've sort of reproduced the table that's in that figure over here. Actually, the figure is much nicer than what I'm doing here, so I encourage you to check out the figure. So a of y, for example, for squares is s of y squared. What is s of y? Well, s of y in this case refers to the width of this infinitesimal rectangle, right? So this will be s of y. So now that we know a of y is s of y squared, and we know what s of y is, let's go back to our region and actually calculate s of y, because we have some formulas for the functions here. So if I'm looking for this width of the infinitesimal rectangle, and that's s of y, right? Remember that this is x equals s of y. It's a function of y. So I'm going to do the rightmost width, and that goes all the way, as you see, to the line, which is x equals y. So that's y. And then I'm going to subtract the leftmost width, which goes all the way to this curve, which is this one. So subtract that. So this is my s of y. And I'm going to then go back over here and remind you that for a square, a of y is the square of s of y. So my volume here, a of y, is the square of s of y, right? This is for a square, so now I'm doing part A of this problem. Part A, my volume is that, and I just found my s of y over here. So that's y minus cubed root of y squared dy. That's it, right? This problem just wanted me to set up, but don't evaluate, the integral for these different volumes. So I found that over here, so great. Now I'm going to make more room for myself and you erase certain things here, and then basically do this all over again, but for a different type of cross section. Okay, next cross section we're working on over here is part B. Part B says cross sections parallel to the x-axis are semicircles. So I already have, I'm not changing my C and D value. So this is the formula that I'm going to stick with for part B as well. But I am changing my cross-section type, right? They're semicircles. So I'm going to scroll over here again, and let's take a look at what happens for semicircles. The area of formula is pi r of y squared over 2. So what is r of y? Well, r of y is kind of the radius of your semicircles, right? So if I go back to my region over here, and I'm looking for, and I have this infinitesimal rectangle that's going to be the base of my semicircle. Imagine a little semicircle drawn above it. Then the radius is going to be half of that width. So the radius is what we had called before s of y divided by 2. Right? So remember that s of y for us was y minus cubed root of y. So that was s of y from a minute ago. And now I'm dividing that by 2. That's going to be the radius, this little tiny radius that is going to be used to generate this semicircular cross section. So that's my r of y. So I'm going to go over here and say a of y is pi over 2 times this particular r of y, so this divided by 2, and then over here on the right hand side squared, right? So right, this is basically pi r squared, which is the area of a full circle, divided by 2. Why divided by 2? Because it's a semicircle, right? So I'm making little semicircles here to draw my solid, to generate my solid. Okay, so that's it. That's, oh, forgot the dy. That's my integral. So I'm not going to touch that. Don't have to evaluate it. I just have to set it up. Okay, so now on to the last part, part C. So part C asks me to look at equilateral triangles. So I'm going to go over here and same deal, look for my formula for my equilateral triangles. So that's the one over here. And this is my formula. So in this case, a of y is root 3 over 4 times s of y squared. We had already found s of y, right? So that's why I did the squares ones first. S of y was y minus cube root of y. So my a of y, I put this in here, and gives me root 3 over 4 times y minus cube root of y, all of that squared. And that's what's going to go, so part C now, that's what's going to go here in my volume formula. So y minus cube root of y squared dy. And that's it, right? Don't have to evaluate that further. Okay, so, and as a picture, right, which I think always helps, here is the width of my infinitesimal rectangle. It's been the same width in all three of these ABC problems. Now I'm doing equilateral triangles. So this same width I'm using as the length for a triangle. So that's my equilateral triangle. And my solid would kind of like have all these little equilateral triangles here. And so, you know, you see it would look something like this, but if you zoom in here, this is really the square one, right? So all these are squares. So this is back to my first part in the problem. This was the part A figure. Okay, so we have done everything. We found the square, the semicircle, the equilateral triangles. And if you zoom in on the right-hand side here, you can see that all that changes really is a of y, first observation. The formula changes. But notice that in all of these formulas, you need to know s of y. So here's s of y, here's s of y. And even for r of y, like we talked about, r of y is half, because it's a semicircle, half, right? Back to our picture, oops, over here. This is the width, and r of y was half of it, because that's the radius from which we constructed the semicircle. So as long as you can find s of y and use these formulas, you can find all the other areas for the cross sections that you'll need, assuming they're one of these three types.